Welcome to Gen I Pulse, your daily tech update. We're discussing what NVIDIA claims is, well, the next generation of accelerated computing infrastructure, the Vera Rubin platform. This launch is framed as ushering in the AI factory era. And it's not just one component, but 6 co-designed chips, the Rubin GPU, Vera CPU, NVLink 6, ConnectX-9, BlueField 4, and Spectrum-X, all engineered to work as a single unified system.
And the claims attached to this launch they're genuinely seismic. They suggest massive, almost unbelievable generational leaps. We're talking about figures up to a 10x reduction in inference token cost and requiring 4x fewer GPUs to train some of the largest, most cutting-edge mixture of experts, or MOE, models compared to their Blackwell architecture.
Exactly. And those figures force an essential question on the industry. Do these advancements represent a fundamental, structural transformation, a true paradigm shift in AI infrastructure, where system bottlenecks are finally solved? I contend that these radical performance claims are entirely justified because Rubin is the first true, fully optimized rack-scale supercomputer, where this extreme co-design across all 6 chips finally eliminates those system-level bottlenecks that have limited our progress until now.
I appreciate the magnitude of the technical achievement. I really do. But I have to anchor the discussion in, practical reality and historical precedent. I believe those dramatic 10x and 4x figures are highly specialized benchmark wins, narrowly optimized for communication-intensive workloads. For the broader range of general-purpose training and inference, I suspect the real-world efficiency gains, while still significant, will prove to be much more modest and incremental than the marketing suggests.
Okay, well, let's start with the architectural philosophy because this is where the foundational shift really occurs. The platform fundamentally changes the economics of AI production by treating the data center, not the chip, as the unit of compute. This extreme co-design is, I think, the only path forward for modern scaling, especially in the age of MOE. Look at the centerpiece, the Vera Rubin NVL72 rack, which integrates 72 GPUs and 36 Vera CPUs.
It is engineered for unity, absolutely. But let's clarify what that system unity achieves versus what the component itself offers.
It achieves a system efficiency that component boosting just cannot. The claim that this configuration requires 4x fewer GPUs to train a colossal 10 trillion parameter MOE model on 100 trillion tokens within a fixed 1-month window is empirical evidence of solving that system-level overhead. You can't reach that level of training compression by simply increasing raw T-flops. You have to remove latency and coherence barriers. The Vera CPU, in particular, acts as an essential component here. It features 88 custom Olympus cores and, critically, 1.8 terabytes per second of coherent NVLink C2C bandwidth directly to the Rubin GPU.
And that's a powerful engineering achievement, no doubt. But I come at it from a different way. When we look at the raw component specs, we see something impressive, but not necessarily an order of magnitude leap. The individual Rubin GPU's training performance is 35 pflops NVFP4. That is an enormous jump from Blackwell's 10 pflops NVFP4, a 3.5x improvement. If we were just comparing components alone, 3.5x is fantastic progress, but it certainly isn't 10x. The 10x figure, therefore, must be derived entirely from system efficiency gains related to communication and utilization, not raw computational power.
That 3.5x component leap is significant, but it highlights precisely why we have to shift our focus from the component to the coherent system. The old architectural model dictates that component speed is capped by the slowest element, often the CPU handling data orchestration or the I/O fabric. If the GPU is waiting for data, its pflops utilization just plummets. The Vera CPU is a high-bandwidth, low-latency data movement and orchestration engine, ensuring the Rubin GPUs are always fed, effectively eliminating that CPU-side bottleneck and maximizing utilization across the entire rack.
I'm not convinced that maximization translates universally, though. The 10x lower cost per million tokens for inference, while a great headline figure is explicitly tied to a very narrow, demanding scenario, the Kimi K2 thinking model using 32K input and 8K output sequence lengths. That is a long context reasoning heavy benchmark designed specifically to stress communication and memory capacity. For the vast majority of existing, simpler inference workloads, critiques of the provided chart suggest the efficiency gains are much closer to the 2x to 4x range, not 10x. If the headline claim is only achievable at the very edge of performance, it makes the platform's return on investment harder to justify for standard AI adopters.
I see why you think that, but I would frame that specificity not as a limitation, but as the necessity of the next AI paradigm. We are rapidly moving into a future dominated by long context models, multi-turn agentic reasoning, and highly sparse MOE architectures. These are communication-dominated workloads. The generational leap is driven entirely by removing those barriers. So the performance benefit is concentrated there, because that's where the architecture is intentionally focused.
Then let's talk specifically about the infrastructure that enables this focus, the interconnect. It's certainly a masterpiece of engineering, but it's also, I think, the engine of complexity.
It is. NVLink 6 delivers 3.6 terabytes per second of GPU to GPU bandwidth. That's double the prior generation. And the NVL72 rack is stitched together by a massive, coherent scale-up fabric providing 260 terabytes per second of all-to-all bandwidth. That 260 terabytes per second is a colossal amount of data throughput. It's the difference between a dirt road and a 12-lane highway for MOE routing. This uniform connectivity is absolutely essential for dynamically routing tokens in MOE models, minimizing stragglers, and preventing job failure due to latency imbalance.
I agree that the capability is groundbreaking, particularly the 2x higher throughput for all-to-all operations, which directly benefits MOE. However, I would frame the reliance on this bespoke interconnect differently, as a significant increase in operational complexity and, frankly, potential vendor lock-in.
How so? The system is designed for maximum performance continuity.
Well, to manage 72 GPUs as a single, coherent system requires incredibly sophisticated orchestration, and it all relies on NVLink 6. If a user isn't running these specific, complex, communication-bound MoE models, or if they're using simpler, highly parallel training jobs, the immense investment in the full NVL72 system and its scale-up fabric becomes overkill. Furthermore, this level of coherence and dependency on a proprietary interconnect means the complexity of debugging, maintenance, and future upgrades is exponentially higher. You are entirely dependent on the specific software stack provided, like CUDA-X and NeMo, to perfectly manage this intricate communication fabric. That complexity is a very real factor in total cost of ownership.
And that's where the architecture's third pillar, the BlueField 4 DPU, comes in. This DPU offloads all the necessary infrastructure services, security, storage management, telemetry, from the Vera CPU and Rubin GPU. By freeing up the primary compute elements, we ensure they focus entirely on token production. We are maximizing goodput, which is the amount of useful AI work completed. This is industrial-scale rigor. You simply cannot achieve this level of reliability and throughput consistency without this co-designed offload capacity.
I appreciate the vision of the AI supercomputer, I do. But let's pivot to the practical side of achieving that promised 10x inference efficiency. I'm sorry, but I just don't buy that it's widely achievable or sustainable without perfect operating conditions.
Why not? When the hardware is designed specifically for these modern bottlenecks. The Rubin GPU, with its 288 gigabytes of HBM4 capacity and 22 terabytes per second of bandwidth, addresses the memory limits directly. And, crucial for agentic AI, is the new inference context memory storage, partially powered by the BlueField 4 DPU. This storage is specifically designed to persist and share KV caches across multiple inference steps efficiently, reducing recomputation. This persistence is stated to boost tokens per second by up to 5x for agentic workloads. This fundamentally transforms long-chain reasoning from a premium, high-latency operation into a cost-effective, scalable service.
That's a compelling architectural path for multi-turn reasoning, but the efficiency gains are tied to a massive variable that isn't always within the operator's control: power and thermal management.
The entire design hinges on aggressive power management and warm water direct liquid cooling at a 45 degrees Celsius supply temperature, which admittedly saves significant parasitic energy. But the data on synchronized AI workloads demonstrates they cause megawatt-scale power ramps and dynamic spikes.
And the platform is designed to handle this. It includes multi-layered power smoothing and energy buffering built right into the rack design to manage those inevitable spikes, ensuring continuous operation.
But if the facility integration isn't flawless, or if the operator's external power grid or overall data center power usage effectiveness, the PUE, constraints force them to throttle the system during those spikes, the expected efficiency gains vanish. Operators will be forced to operate below peak capacity, negating the tokens produced per unit of energy. The theoretical maximum efficiency is highly fragile when faced with real-world power provisioning limitations.
I think you're confusing the necessity of industrial rigor with a flaw in the design. You can't move to continuous, always-on intelligence production without these advanced power management systems and the operational framework to support them. The focus is on maximizing goodput. You need those systems, like mission control and the autonomous recovery engines, to minimize losses from job restarts or hardware stragglers. The complexity is inherent to the scale of the solution, not a bug.
I would argue that the operational requirements of this full AI factory stack introduce a new layer of highly specialized hidden cost that isn't captured in the simple 10x token cost metric. Operating mission control, integrating the liquid cooling infrastructure, and managing highly dynamic power consumption demands highly specialized, expensive engineering teams. This specialized talent and the vendor lock-in introduced by relying on the bespoke software stacks must be fully factored into the total cost of ownership equation. When you consider those operational expenditures, the advantage shrinks significantly for any customer whose primary workload doesn't align perfectly with the MOE or long context benchmarks.
But that's the point of the integrated design, including features like the cable-free modular compute tray, which simplifies assembly by 18x. They are minimizing maintenance complexity to offset that operational rigor. Reliability, availability, and serviceability, RAS, are fundamental to scaling efficiency. The design is a holistic solution, addressing the cost of downtime and maintenance, not just the cost of computation.
The modularity is excellent for RAS, sure, but the core 10x claim hinges on a perfect storm: long context, communication-heavy workloads, running in an environment where thermal, power, and software constraints from NVLink 6 orchestration to mission control are managed flawlessly. This suggests that 10x is the extremely fragile ceiling, not the robust everyday average. If any part of that complex stack fails or requires throttling due to facility limitations, performance risks collapsing back toward the 3 to 4x component-level improvement.
My stance remains that the Rubin platform represents the necessary architectural evolution required to move beyond current AI bottlenecks. By moving past component optimization to true rack-scale co-design across all 6 chips, it addresses the fundamental system-level barriers, coherence, latency, and orchestration, that limit the scaling of MO and agentic models. This is a foundational shift in how intelligence is produced at scale, transforming disconnected clusters into unified, industrial-grade supercomputers.
That's a compelling argument for the future of AI. But while the engineering brilliance behind the 6 new chips is undeniable, the practical reality for the broader market suggests a more careful and likely incremental adoption curve. The exponential claims are constrained by those highly specific benchmarks and the immense, costly complexity of operationalizing the full AI factory stack. The true test of this architecture will be measured in 2 years. How far outside those benchmarked communication-heavy workloads does that 10x efficiency truly extend across the general ecosystem?
It is a fascinating tension between theoretical maximum performance unlocked by architectural coherence and, the logistical challenges of achieving that maximum at industrial scale. The industry is currently debating whether the juice is worth the squeeze on infrastructure.
And that is a complexity our listeners must fully grapple with as they evaluate their investment strategies. There is clearly much more to explore in the material when the real-world operational data begins to emerge in the second half of 2026. This has been Gen AI Pulse.